Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with learnbay.co. Happy learning!
Okay, so answer me one question. What is a feature? In machine learning, what is a feature? So there are two terms usually, parameter and feature. So what are these two if I ask you?
Feature are the basically columns of the data, and parameters are the weightages of that column.
Makes sense. Yeah, very good. So you can say features are something that are being provided by data. So this is your data. And parameters is something you have to estimate. This is estimated by, mostly this is estimated by ML algorithms. Okay. So features are something that is already provided in data, xi, these column values that you see, and theta I is estimated by your ML algorithms. Okay, now depending on which kind of algorithm you're using. Now the problem is not all the features are actually required, or many times a lot of features do not make sense to work in togetherness. Okay, so there are different reasons why we should not use a lot of features. The very first reason is, so what we are understanding or trying to understand is called feature reduction or dimensionality reduction. Okay, so what we are trying to understand is feature reduction or dimensionality reduction. So why we want to do this? Or feature selection techniques, you can, like, there are different ways of saying this. So what happens is sometimes extra features can actually add complexity rather than reducing complexity. They can add to the complexity of the algorithm or complexity of the overall data. And while separating or passing a regression line or a curve through them, the performance actually might get worse. So just adding always extra features doesn't work very well. Have I explained you the curse of dimensionality?
No.
Okay, no problem. Then we will talk about this right now. What is curse of dimensionality? So look, what happens is, okay, so I will ask you to remember your gradient descent, okay? Everyone is comfortable here around with gradient descent?
Yeah.
Okay, very well. So fundamentally, what is gradient descent, if I may ask? Let's say if this is j theta, and let's say if this is theta naught. So based on some error function, let's say if this is kind of a parabola, and if you randomly start somewhere, you start taking steps to minimize the overall loss. And let's say this is your optimal point. Okay, cool. Everyone can see this?
Yeah.
Okay. Now, what if I say actually the change is not happening in this curve, the change always happens here itself. The change always happens here. Do you agree with me? It is just the theta that is changing. Actually, nothing is happening. No change actually happens on this curve. Computer actually doesn't even knows what this curve is. Based on a certain value, that is basically the derivative, the gradient. Okay. So by dou j theta by dou theta naught, it tries to get a gradient at every step based on that feedback, that whatever amount of gradient it gets. So the idea is here, somewhere here, the gradient will turn 0. Okay, because if you are parallel to x-axis, your gradient will, because tan 0 is 0 basically. Okay, tan 0, sorry, if it is 0 degree, then it becomes 0. Agree?
Yeah.
Yes.
Okay, So what if I say, because look, because you are just searching in one axis so far, so you just have to worry about theta naught here, right? But what if there were 10 theta naught to theta 10, so total of 11 axes on which you have to optimize, plus a j theta that was a separate axis, let's say. That was for designing anyways. What is your maximum what is the complexity level that you're looking right now? By how many folds you have just increased your complexity?
Number of combinations of this?
But how would you get that combination number, if I may ask?
Like how theta not dependent? If I change theta 1, how theta not behaves? If I change
Yeah,
theta 1, how
exactly.
theta 2 behaves? Something like that.
First assumption, let's say, okay, let me make this assumption, although this is not right, not true. But yeah, even in linear regression or all things, basically we do assume the features are independent actually. So we try to assume that these thetas ideally should not have a direct impact on each other. But that can fail and we will have to put a filter to maybe reduce that problem as well. But we ideally assume features are independent of each other. Okay.
Okay.
Okay. All right. So let me explain the idea. This is kind of a philosophical idea as well. So what is cursive dimensionality? So the idea is, given more choices or more accesses or more information, there's no guarantee your system is always going to make better decisions. Okay. That is the very dicey thing to say. Okay. So let's say, okay, so you start at 0 and this is 1, 2, 3, 4, 5, 6, 7, 8. Now at one point, remember, at one point you can only take one step. Okay, one step. So can I ask you, if I have some n to search, some arbitrary n, what is the worst time complexity it can take to search or reach till n? Let's say if there is no intelligent method to reach to n, if it is literally the brute force idea, then what is the worst time complexity it can take?
And itself.
Very good. Big O of n. So this is linear, right? This is linear, so no problem here. Now let's expand this idea a bit. Now let's go into two dimensions. And now again some arbitrary n has, now actually this time some arbitrary n into n cross n has to be found. Let's say both are n. Okay. And now you can only move into one cell at a time. So imagine this as a one cell and you can think this as a chessboard and you can only move one cell at a time. So now what is the worst time complexity to reach to n comma n?
N square.
Very good. So right now you can see it has become n squared. Now what is the time complexity if I put another axis? And now imagine you can only move one cube at a time.
N
So
cube.
yeah, very good. So in this scenario, it can reach till, of course, this is worst case scenario. So you see, if you keep increasing the dimensions or number of dimensions, and if you were to try to optimize for a curve, now you have three things to optimize for. Okay. And you will be worried about all the gradients and how the system is moving. So the idea is, the bigger the function or the more dimensions you involve, maybe your classification area line becomes clear, but optimization becomes extremely hard as you have more dimensions. And this is called cursive dimensionality. Do you guys also feel this, that in the age of e-commerce, where you have like, when you even search for a t-shirt, you have like thousands of options? Do you also feel that sometimes I know it is also a personality thing, it's not very common for everyone, but still, in a statistical regularity term, I want to talk that do most of you feel that actually by looking at more choices, you get even more confused, or it even takes much more time to decide whatever you want?
Yeah, absolutely. Not
Yeah,
to just
if
learn.
you are given like infinite choices or very large amount of choices, which let's say e-commerce sites like Amazon, Flipkart are providing us. Okay. So sometimes when even you start looking for a t-shirt, the search goes on and on and on. Okay. So this is the curse of dimensionality. Okay. Maybe in high dimensions, it is easier to classify, okay, or regress. The problem is the algorithm becomes really complex, or the overall runtime also becomes too much. Okay, so this is called cursive dimensionality, and as you increase the dimension, so if you had 11 dimensions, the worst case scenario is like this, and that is not something very pretty. Okay, big O of n to the power 11 is not something you want, but this happens. You have seen a couple of data sets where we had even much worse dimensionality than this. So remember, just having more dimensionality doesn't solve the problem. So idea is, just because you have more features, it doesn't always makes our life easier. Some features can actually complicate or might not give the results that we want. Okay. This is clear. Sorry, this is clear to everyone.
Yeah.
Yeah.
If you have any problem, please ask me. I understand. This is for discuss first time. So yeah. So if you feel that this is not something you're comfortable, I can again repeat. But just trying to explain you, like just putting more columns or more data doesn't always makes our life better. Okay. Okay, guys. So if I assume this is okay with all of you.
Yeah.
Wonderful. So to do feature selection, and this notebook is about all about basically feature selection itself. Okay. So we do have in sklearn itself, we have something called feature selection. Now sklearn is like, as you understand, is a go-to library that we use almost for anything. Sorry. So there is a one important process that is called feature selection, and sklearn has a complete like module for feature selection itself. Okay. So there are a lot of things, and we will like to discuss them in bit brief. Okay, I don't want to go in complete details all the time, but still basically we will try to deal with some information that we need to understand, and we need to understand why we need to drop these kind of columns. Okay. Okay, the very first technique that we will study right here is called variance threshold. Okay, so there is something called variance threshold that is okay. So let me explain what variance threshold behaves or how it works like. Okay, so let me take an example here, and let's say if there is a employee data. Okay, if I have employee data of the same company. Okay, and imagine there is a column called company name, and of course there is another columns like name of the employee, maybe salary. Okay, what is do you find that like term like company name, which might be same for almost all the employees here anyways, does it adds any value here?
No, obviously.
Yeah, no, right there. So there are columns sometimes present which don't actually add any value to the system or to the outcomes actually of your prediction models. Okay, so those can be removed. So the idea is we need to drop the columns whose variance is below some configured level. So let's choose an idea. So here, if you look here, so this is the data frame that we have created, and let's say there are three columns A, B, C. Okay. Now by applying label encoder, we will just make sure that everything is in numerical terms. Now, what do you see with A exactly? So A is about gender, like male and female.
There is not much of variance.
There is not much of variance, right? It is almost same in most of the cases. It is so if we were to go and apply feature variance threshold, and you will have to choose this threshold, okay? And let's say you put 0.2. So the idea is if your variance threshold is less than 0.2 for whichever column, that column can be simply dropped. So it will do fit transform, okay? And like it will drop that column itself, okay? So you can choose the rule feature selection variance threshold as 0.2, and it will drop that column. So you can see the first column is actually gone here, and it can also print out the variances if you want. So it will show the first column variances this much, 1099375. These two are 0.5, 0.5, which is pretty good to be honest. So usually we do select thresholds as like 0.15, 0.2, 0.25 at max. Okay, usually we don't usually go beyond 0.25. Okay, all right. Now, but this technique might not always work for non-numerical classes. So there is something called chi-square for basically test. It is kind of a test of independence. Okay. So what is chi-square? So let me give you the simple idea. Chi, or many times it is represented by a symbol almost like X, but it is not actually sky. I might not be writing it correctly. So it is called chi-square test for independence. Now this actually works for categorical values. Why? So the variance and other tricks are actually working for your numerical values only. So over there you need to have numerical systems. Okay. But chi-square actually works for mostly it is utilized in cases where we might have categorical values, because basically it depends on the count. Okay. So how do you calculate chi-square? So chi-square is simple. Basically it says chi-square is nothing but summation of observed minus estimated. So observed is the true value. You can think this is true and this is your prediction, pred squared by again estimated. Okay. So some people might also look like, especially for a sample, people write it like this. So I is equal to 1 to k, and observed minus expected squared expected. Okay.
Sir,
Mm-hmm.
this feature reduction technique are you performing before applying model or after applying
Yeah,
model?
this is tricky actually. I didn't wanted to answer this before like I finish this. Okay, so this goes in very tricky after a while. So as you might understand, it is not like a one-way street. Okay, I might have shown you that picture while we were going through data pre-processing. Remember? So do you remember there were loops actually over there? So when you are doing data pre-processing, and this could be called a part of data pre-processing itself. Okay, and then you can train your model. Problem is, and especially after validation, if your model doesn't work very well, actually you have to come back if you want to try and train some other model. So remember, like in the trees and your random forest, normalization is not required, right? I'm just simply giving a data pre-processing example right now. So normalization is not required, is it? Everyone?
Yeah.
But in linear regression and SVMs, which are more distance based, I have told you, you have to normalize or scale up your data, right?
Yes.
So it's not like I'm trying to tell, it's not like a one-way street. You cannot always pre-decide that this is what I'm going to do all the time. Many times it also depends. And I will also show you some feature reduction techniques, which actually depends on models. Means you have to at least use one model, and based on that value, it will be able to tell which columns might not be helping you too much. So it's never one-way street. You have to kind of recursively try this approach. So you go from data pre-processing and you can take feature reduction in that part itself. Then you train your model, then you validate it. And if the validation results are not that great, again, you go back to data pre-processing. Again, you do and maybe try to do feature reduction in a different way. Again, you train the model, again, you validate. So it's kind of a loopy system that it is kind of doing it again and again till you get the best results. Does that make sense to everyone?
Yes.
Okay. So yeah, this is why I didn't wanted to mention at the start because it can confuse people. Okay, guys, remember now the feature data should be Boolean or count, either 0 or 1 or count value. So the point is, what I'm trying to say, ideally it would be better if we have categorical values itself. Okay. So it's a very simple thing, feature selection.chi2, and you will have to ask like whichever columns you want, and it will throw chi-square values. Okay. So the idea is very simple. The higher value means more important feature for target. So with compared to target, whichever gives you higher feature selection value, so that is more important. So if you remember with your regression time or regression values like Outlook, so this is just basic label encoding. Remember, even in entropy, which was the best category here or best feature here?
Outlook.
Outlook. If you remember, Outlook actually was more important than anything. If you could figure out Outlook compared to play, which is just 0 and 1, it was easier. So here we just want counts. Okay. So this observed minus estimated is just count. How many number of observed minus estimated divided by the total estimated. This is chi-square. So again, remember here the higher value is better. Even here in variance, you need to go close to 1 or as close to 1 as possible. Anything very small like 0, 0.1, 0.15 is something that we like to not use because then we understand the variance is not that much and it might not be, this column might not have almost any impact on the outcome. Okay. Now, although this F classification is not that regularly used, it is better to just stick with chi-square itself. Okay. But we do use F classification. It is kind of an ANOVA technique, but not everyone actually uses it. Okay. Again, remember it also requires. Now this will work feature variables which are more continuous in nature and target value is still discrete. So mainly for classification. So basically this method uses the ratio of variation within a column and variation across the columns. So you will get the feature selection F classification. So it returns two things, chi-square and p-value. Okay. Like it is just a chi-square. You can understand it's just a chi-square for numerical values. That's all it is. And again, same idea, whichever is bigger, whichever number is bigger, that is more useful. Anything like 0 needs to be eliminated. So the columns with throughout 0, you can just immediately eliminate, or again, you can put a threshold. You can put a chi-squares threshold here and maybe say anything less than 40 should be gone. So if I put a threshold of less than 40, which columns would be gone or how many columns we will lose?
Six of them.
6 of them. You will lose this. Okay. Then again, you will lose this one, this. Yeah, 39 is also gone. These two are also gone. Okay. And if you keep 100, even more number of columns will be gone. But remember, after a while, the performance starts, you cannot just keep dropping all the columns. So that is the tricky part. Like you will have to stop somewhere. Now, similarly, there is something called F regression angle. Okay. Now, whatever we were doing, the target variable was discrete. So we understood it's a classification. What if you wanted to do it for regression problems? So you run something called F regression, very similar as ANOVA technique. Again, it will give you F values. And again, you can select the higher values or larger values as selected features, and anything which is very small, you can just eliminate that. Okay, although everything looks like very important here, it will be very hard to drop anything here if you look carefully. But you can very easily tell the first column definitely is most important. So you cannot drop the first column here. So the first column, if I remember correctly, is usually square footage area. So whenever you are trying to determine the outcome of the house pricing, area does tends to have a highest value or impact on the final outcome. So understood? So look, just to give you a brief rundown. So chi-square use when everything is discrete. The features are discrete and the target is discrete. Use the F classification when internal x values are numerical, but the target is discrete. And when you use F regression, when everything is numerical, your data is also numerical and your target is also numerical. Make sense? So just giving you simple rules to kind of navigate this, otherwise it becomes a bit tricky after a while. But remember, F-test only captures linear dependency. Okay, anything non-linear cannot be caught by F-test. But anything which is linearly correlated or linearly related with the outcome, that can be caught very easily.
So one question.
Yeah, go ahead, go ahead.
So the question is that there could be 2-3 features which might not be varying much. Yeah, but within them there's a relationship. So for
I will
example,
talk about that multicollinearity, what you are just talking about right now.
okay, might be that. What I was saying is, if I take the heat sensor in the car, which is there, it's always C or slightly above C or mid of C and H. So so throughout my life, I'll only see C and H, but when it goes to H, that is when the danger is. So I can't drop that column. Look, I'm just thinking aloud.
Yeah, that was basically going to be my last point, that at some point, even if you have all the statistical techniques, so I have talked to you about the causality problem, right? Like this is why we had to talk about that. Even if you do not see causality as a major discussion, sometimes this is what a domain expert or subject matter experts knows, right? The way what you are saying is correct. Everything is not statistics. Look, statistics is mostly correlation, right? Mostly trying to find these correlation between different variables. All of the tests that we are running, regression, F test, F classification, means chi-square, F classification, F regression, they are always trying to capture some kind of a linear dependency, right? Between the data and the features. But we have talked about this already, that there are hidden variables internally as well. Just because you can always figure out a correlation, it doesn't mean causality is also understood by you. So yeah, there is that path that you should not always just start trusting statistical methods to the hilt. Okay, let's use that word. At some point, you have to be cautious with your approach, and you also have to think as a domain expert and subject matter expert. Maybe it is some other person in your team, or it will take some years of experience for you to become a domain expert to really understand what I'm trying to tell. Okay, that at some point, even as you give the rightful example of C, that the temperature usually doesn't comes down, but when it will come down, that's where the car will stop. And let's say if you were to trying to do anomaly detection or something, you just can't drop that column, because that's how you can also realize that the car might stop or car will stop very soon in the future. Does that make sense?
Yeah, sure.
The same thing one of my friends was telling. He's working in kind of electric cars. Even in India, like a lot of startups have popped up which are developing electric cars and scooters, right? So he's using a reinforcement learning method, and I was talking to him about how to optimize about it. And he was telling about the temperature, that batteries can also burst, right? You know that the battery, these lithium ions,
Yeah.
if you go beyond certain temperature, they will just burst or catch fire. So that should not happen. So they had to even put sensors on the batteries itself to measure the battery's response. So most of the days it is in ideal temperature range and nothing happens. But if you forget to put sensors, or if you forget or somehow even if their correlation is very low with some target variable, we just don't drop the readings from the battery. Otherwise, it will catch fire or it will blast or do something really damaging to people. Okay. So yeah, that comes from the understanding of causal model, that how things work. So even if your F test and these things are giving, and that was like my last point to make actually over there, that even if all the tests are there, but as a subject matter expert, if you feel this column should be there, then you get to put it. I'm not saying that just because statistics has shown you that it is not important, you eliminate it, because you understand, you might understand some core causation problem that might be happening if you completely forget about that column. Does that answer your question?
Yeah, it does. Thanks.
Okay. And then there is a mutual information problem, but this better information is, or basically I will tell you. So basically what is mutual information is, or you can try to understand it. So let's generate a completely two curves, okay, X and Y. So X is completely random and Y is nothing. It is like X values and some sign values around it, okay, and some randomness. So if you were to choose F regression, and let's imagine it as a regression problem, these are the values you are gonna get, and you will realize initial two columns look very important and rest of them are not that important, for now at least. And this is what you can see, that this is how it is looking, the first one. But once you plot the Y basically internally, this is how it will start to look, that you will see there is some information, or there is some information connected, especially with Y. So you cannot, even X looks random itself. Okay, you can say maybe X looks random itself very much right now. You can say that no, there is some mutual information that has been provided by it. So mutual info is nothing, it is just a dependency, that how much Y is dependent, okay? Now, mutual info is better than correlation. Why? Because correlation can only target linear connection. But mutual info actually can target dependencies even if it is non-linear. But yes, you will require a target to be continuous. So you can get, rather than running your correlation, you can also run correlation, but the problem with correlation is it always targets linear relationship. Remember, correlation, I might have given you that idea in correlation, that you can always connect the information only when it is linearly connected, otherwise it can't really figure it out. But mutual info regression or mutual info classification, again, they will return the values between 0 to 1. So there is no negative part, and they can capture the dependency even if it is non-linear. Okay, so this is a bit better compared to your correlation. So again, you can build and you can do any of these things. You can run mutual info regression for X and Y. Again, remember, the higher the value, it better it is. And similarly,
one question. Actually, there is something called as a Pearson correlation and Rankine correlation also, no?
Correlation, yeah.
So that can be used, right? Is it the same thing? Information.
Sorry, one sec. Can you say that?
So basically, when we use correlation coefficient function in here Python, so which of these
is always
three?
Pearson. That is always Pearson.
That is always Pearson. Okay.
Yeah.
There are actually three, no? Spearman something.
Yes, Spearman. But because we have not covered them, so I'm not going to go in that direction. But mutual info, if someone is interested, I will just simply give you basic information that the equation looks like this. So mutual information is again the probability idea. So if I'm remembering it correctly, so probability of X and Y, X to S comma Y log of, again you can choose your log terms, P of X, Y, no, sorry, my bad. One sec guys, one sec. So mutual info X comma Y is, so X is your target, sorry, X is your input, Y is your target. So X are the independent features, Y is the target. Summation of probability of x comma y power, actually it is power, that is what I was getting confused with, into log of, everything is in power, okay, p of x comma y, again power of x comma y divided by log of, sorry, px of x into py of y. So the equation looks a bit complex, but basically this is your overall idea, that this is what mutual information ideally looks like. It is also called something called conditional entropy. Now you don't have to study this, it is not really required, but just I wanted you to know. So this equation is called conditional entropy. So some people might think like there is some resemblance with entropy, and you are right, basically there is. Or you simply call it mutual information. And this is far better than your Pearson correlation because it can capture nonlinear dependencies as well. Okay.
So could you please repeat? I was disconnected. What does M and P stands for?
M is mutual information, P is the probability, conditional probability of x given y. So this is mutual information.
And the denominator? Px.
P of x and this is P of y.
Okay, it's simply the probability of x, right? In the bracket
Yeah,
we have mentioned.
probability of x. Yeah, you're right.
Sir, what is x comma y? As in on the power? I
Addition.
understand. No, that I understood. P x comma y I understood, but on top you said written x comma y and then log. So what is that on top x comma y? Is it a function?
You can take
Not
it like
this. No, not this. Before that, log. Before the log, you have got x comma this one. What is this? There should be some probability or function or something. Like just x comma y. I was thinking, what is this?
yeah, so it is like x given y over there, like how much is the value over there. So that is x given y. Okay, if you want me, I can basically simplify this one. If so, you can think it like this. Okay, basically it is nothing but conditional entropy is like either it could be y given x, mostly it is y given x. Okay, so rather than taking that complicated formula, maybe let me give you a slightly less complicated one. Means you can derive it to this one. And y belongs to set of y. So this belongs to set of x, and this is your probability of x comma y to log of probability of x and p of x comma y. This is easier to understand. Those are just notations that way I know like that might look confusing, but if you wanted to understand, this is the most simplest way of understanding this.
Could you please repeat? What is h y to y given?
Mutual, this is, you can say it is conditional entropy, which is again just mutual information anyways. Okay, y is your outcome, y given x is nothing but probability of x comma y into log of px by p of x comma y.
Clear, sir.
Okay. All right. Similarly, so that was for numerical values. Similarly, we can do it for your, let's say, connection ones, and wherever we have this connection. So over there, what we can do here is, and maybe because no, we are not reading CSV from here, is it? Maybe it is just data right now. Actually, right now it is in my local folder, so that's why. Okay, so basically you get your salary value. So first, let me show you this data actually, so that we can run this and see all of this. So I hope the folder is the correct one. Yeah, PD is not defined. So, okay. Okay, it started from directly from there. That's why. Okay. Let's start from here. Otherwise, it will keep on running. Okay. Now it ran. Let's see if this is working. Let's see. Okay, so let's put one just to first show you the data. Otherwise, it will not make sense. So what is this adult data? Okay, it is information about people basically, and their various features are being provided, and their calculation of taxes and capital gains and everything, and how much they make basically. Okay, and which country they are from and stuff. So again, if you had to perform anything like so right now, even it might look like a regression, basically it is a classification. Okay, why?
We are dividing them in groups like less than
Groups
50k.
less than equal to 50k, more than 50k, more than 100k. So this becomes a grouping scenario. Okay, now this is tricky, right? To handle such data is very tricky, that you can see there are some numerical values, but most of the values are still like categorical. Okay, so first we will have to convert it. So because salary is the outcome, so let's remove that altogether and let's use label encoder for now and just convert the data into label encoding. Okay, and now once they have been converted to numbers, okay, what just happened here? The shape is okay. Could not convert the string to float. Wait. Okay, we will might have to manipulate this one actually a bit. So what we will have to do here is we will have to manipulate this into like multiple categories like 1.0, 2.0 or something. So basically you will have to use your own map to calculate this. So what you can do is less than 50k can get a score of 0. So here you again have to go for a ordering. So what you can do here is you can create a map function and that can hopefully help. So maybe. So what we will have to do is basically we will have to map it with okay. So here you will have to choose, and this will actually take a time. So I will not try to waste too much time. So what you have to do here is you will have to map it to a number. Okay, data, just apply that, and then it will work. Okay, so that will just take a bit more time, but this can be done. So basically, you have to construct a salary dictionary and just provide these numbers 0, 1, 2, 3, 4 in whatever order they are coming, and accordingly you can just apply this, and this should work out. Because it is still expecting the number to be numbers, not exactly as a string. So that's why it is causing the problem. So basically it is trying to expect like some kind of a decimal, and it is finding a string. So that will be a problem. Okay, now better actually. So we may not do this actually. What we can do is based on the configuration. So there is something called select k best. Okay, so the better technique would be actually to go for the k best technique rather than going all by one, but it will take a bit of time. So what it does is based on its own configuration, and I will show you what is feature selection k best. select k best. Okay, so the idea is basically it doesn't actually gives you the highest thing, it just gives you k highest scores. So the idea is very simple, that internally based on its basic setting, it uses either mutual information, ANOVA or regression based techniques, so F score or mutual information, and it provides you the best value output. Okay, so you run feature selection, select k best. Now the major thing that you have to select here is k is equal to 7. So how many features you want finally. Now you will have to provide the score function. So again, rather than applying it individually, what you can do is you can go for feature selection and call the exact function that you want to use. And now by running this, let's say if we run this, and again, you can see we get all these scores. And now we get, if you look at the columns or look at your data, there are only 7 columns left. So it selected the best 7 columns. So based on these scores, it selected the best 7 columns and it let go of everything. Now, based on this running, you can transform your data. And right now we are doing it based on mutual info. Now mutual info is going to take a bit of time, slightly bit more than F regression or F classification. And again, you can do that same for, so now you can figure out most of the days, the columns remain same, almost they remain the same, but there is always 1 or 2 discrepancy points that you can find, that maybe there's 9, this value came from here and then 40 got deleted. So there is some difference between mutual information and F classification or F scores, but more or less for most of the data points, they remain very similar. Or you can also see the rest of the data right now. So it has been converted into that many number of rows into 7 columns only. So now we have been able to manage or reduce the features altogether by selecting k best. So it is, rather than doing it individually, it is better to run k best and just select or just provide whichever function you want to use and just run it from there itself. So it kind of automates some of your work. So let's say if you were to put 10, so it will just, based on mutual info classification, it will select the top 10 features, and on 10 features now you can do anything. Does this make sense? Okay. You can also go with the percentile idea. What is percentile? Anyone? What is percentile?
Is it the same that pandas return under info thing, that 25, 50, 75, 70?
Yeah, simply percentile is what? Forget pandas right now. What is percentile? So k-best is like directly selecting the number of features. There is something called select percentile. Same idea, almost remains the same by choosing the correct function. But when you write 20, what does it mean? Come on, give it a try. 20 is the upper percentile. So what? Okay, so there's not much of a difference, guys. Okay, You use k-best, you use percentile, it doesn't matter too much. In k-best, when you write k is equal to 10, it meant 10 features. Okay? But when here you write in percentile, so by default in percentile also the value is 10. But what does this 10 means? The top 10%. Okay? That's it. That's the major difference. Otherwise, there is not much difference here. So if you're not sure about how many features you should select, you could go for a percentile rule and maybe select top 10%, or when you give 20%. So it could mean the top 20 percentile or 20 percentage. Make sense?
Yes, sir, but the one question, 20, that means 80% will be discarded, is it?
Yeah, that is what's going to happen.
Okay.
So usually how much we put, like 10, 20, is this much of it?
Now that is the recursive problem, right? You don't know this, because now what you have to do is you have to run the model and then see the performance. There is no, how do I say? In this step, there is literally no shortcut. Okay, whatever you try, it has to be run through a model or combination of models in a pipeline, most preferably. You have to do all kinds of model validation, and then only you know, did it work or not. Get my problem? Like what I'm trying to tell you here, that there is no easy way. I will show you a couple of more techniques, where you can almost figure out, like PCN stuff, that you can get a basic idea how much variance. If you know how much variance you want to capture, then I can tell you how many features you should select. Here it doesn't work. Look, some of these ideas are basically only capturing the linear dependency. What if something has a non-linear dependency? It cannot be always captured. So even you might think that, oh, I have taken enough features, but let's say if some feature has a non-linear dependency, and if you were somehow eliminating that, then your results are not going to come well. Or if there was some kind of a causal problem. So the problems are like much varied. It's just not that we figure out correlation and then we are golden. No, that's not how it usually works. Okay, so now there are two things which work with the model only. Okay, so I can explain this in slightly different way. So basically, select from model is nothing. It is like selecting important features from model weights. Now the estimator, whichever estimator you use, it should support feature importances. Now the whole problem is, or here you can put a threshold, like how much minimum feature importance you want. So what it will do is, let's say it runs load Boston and it runs linear regression on top of it, first of all. Now, while running the linear regression, you can put a threshold like 0.25. So let me show you. Okay, so it basically tells you that only 7 columns are more important. The total columns were basically, if you if you want to see it, it's not a big deal. So we can also maybe say updated data. Sorry. One sec. Oh, sorry, what I'm doing here. Sorry, that is already the shape, right? My bad. So maybe I can do something like this. Yeah. So basically this is how it will look like. It will only choose those columns, those are relevant. So as you can see here, that only 7 columns are relevant here. And the original shape, if you remember, was 13. So we basically were able to eliminate certain columns by running from the linear regression well in advance. But as you can see, at least you still had to run linear regression. And this is what I'm talking about, the recursive problem, that you cannot do it many times in a single go. Yeah, do you have a question?
Yes, sir. Like here we first run linear regression, then we reduce the number of columns, and then we can again rerun. So
yeah, you can rerun
when
again.
we are rerunning, then should we have to use linear regression only, or we can use any other model?
You can try any other regression technique.
Okay, but is it like good if I am using some particular model and that regression technique I'm using first, and then only I'm updating the data?
No,
Or
it's not like
I
it has to
can
be
use
tried and tested. There's no one rule that, okay, you start with a simple model. The most simplest advice would be you always start with the most simplest model. Do not go for a complex model at the start, right?
Okay.
Remember Occam's razor that you basically
Yes,
start with the
yes.
simplest explanation. So first run the most simplest thing that you know. So in regression, you know linear regression, which you can call the most simplest algorithm that you know. Run that, find the features, and then you can run it with against complex like a random forest regressor, or even there is SVR support vector regressor, and then give it a try. Or maybe adopt it for a polynomial regression. That can also work.
Okay.
And the final one, although I will tell you not to use this, okay? Recursive feature elimination is like waste of time. Okay, so okay, how it works is very okay. So let me explain how recursive feature elimination will work. It's a brute force idea, okay? There is no beauty in it, basically, or there is nothing very interesting happening really. Let's say you have different features. Okay, and now what you do here is basically use these x0, x2, x3, x4, x6 till and y. So first we will use all the 7 features, and again you will have to use some model. So let's say I am using SVM. Okay, imagine just we are using SVM model. So first we use all the 7 features and get some, let's say 90% accuracy. Okay, now what you do is you create 7 different frames or 7 combinations where only 6 columns are present. So let's say this is x0, x1, x2, x4, x5 and x6. You might have seen I have dropped x3 here. Similarly, in some other it might be present. So how many total combinations I can make here, guys? x0, x1, x2, x3, x5, x6. So here I have dropped x4. So how many total of these combinations can be made?
If you're not looking at the how they're arranged, then as an
Of course, it doesn't matter. Arrangement will not. Like again, if I write my equation like this, theta naught plus theta 1x, or if I write my equation like this, does this makes any difference?
yeah, that's what I'm saying. So then 7, you will have 7 frames.
Total 7, you're right. Now, so recursive feature elimination is very basic. Okay, what it says is, look, do it like this. Get the accuracy values in all cases, and in whichever case it is almost similar to 90, you understand the columns which are missing have almost no impact. Did you get my idea? Let's say even after dropping x3, my percentage point is almost 90%. So what does it mean?
That column doesn't have any impact.
Yeah, it has no impact on one. So now I can eliminate x3. Okay. Similarly, there could be some other columns which might also give you the same result. Now let's choose this one hour as a next test case. So again, it is recursive. Okay, it's not gonna stop. And this is why it is waste of time many times. Okay. x0, x1, x2, x4, x5, x6. Now what you need to do, and again you have y anyways. What you need to do?
It will calculate the accuracy, then it will again drop one column.
No, accuracy is, let's say, already known because it, let's say, it doesn't change at all.
You will create 6 frames now.
Exactly. 6 combinations again. And again, we will try to find certain features which almost have no drop in. So we can do this till we only are left with the columns. Wherever you drop a single column, accuracy changes. Okay. Get the idea what is recursive feature elimination?
Yes.
But it is like a brute force technique and it can take time. So I always do not recommend people to use RFE. You can use it if your data set is small or the features are like 10 features, right? So 50 rows, 10 features, that is doable. Okay, that much I can say, maybe, yeah, you can take a chance. But when you have 1,000 features or like 10,000 rows, maybe not a great idea. What it can give you is ranking. So you can get the ranking of the features. So whichever is one, those features you would not be able to reduce. Okay, whichever is one, those features just can't be reduced now. Anything lower, you can put a threshold that anything greater than 4 or 5, I can reduce. So anything greater than 4 is 6 and 5. So these two columns I can get rid of altogether. Okay. So all 5, basically you can see here the data shape is 5 after conversion. So what it means is all the ones, whichever you can see as 1, these 5 are the final 5 which can't be removed. If you remove these final 5, the values change drastically. Okay. So there is 2 here, 1 here, 3, 4, 5. So these 5 columns can't be reduced. Rest you can let go, and this is what it has done actually here. That when you look here, it has only, it keeps whichever ranking as 1, but you can change that. Okay, you can choose not to do that and maybe even keep some more rankings. But by default, this is what it is gonna do. It will recursively go till that level where it is on the lowest side. Or it is like, okay, if you drop any of these columns, your value is gonna change really drastically. Okay, so again, just to clarify this whole part, okay, there are 3 caveats, okay? It's not always that easy, and believe me, feature reduction is a trick that people need to master. So look, what is the first is, okay, and this is very hard to digest, that is not perfect, okay? Even if you do all of this, it doesn't actually guarantees you that it will always be successful. It's not perfect. Why? Non-linear dependency. So although mutual information can capture non-linear dependency as well. Confounding variables. There could be some hidden variables which you can't see. Okay. Causal problem. So there could be causality issues. Okay. Which many times can only be solved by a domain expert. So if you are not a domain expert and if you do not understand the domain properly, then you can run into these problems. Second is entwined with ML techniques that you use. So there is not a universal way that many people, I think, were kind of trying to understand that. But it depends on which techniques you are going to use at the end of the day. It is not universal, first of all. So it goes in hand with the training. So I do pre-processing, and let's say feature reduction is part of pre-processing. Okay. Then you do your training. And as I said, validation. So training to validation is a single route. But then after validation, if the results are not good, you will have to go to pre-processing. So there is a loop system here that is going on. And you have to work through all the 3 one by one again and again till you perfect, or till you get your perfect match. Okay. And the third, some domains is not directly useful. So if you were to try to do it with a CV problem, computer vision, almost every pixel is a feature and almost every pixel gets the same score. So if you try this in computer vision, it's not going to work out. So if you try to get a mutual information, or if you try to get a feature importance or anything, so almost all the pixels give you the same score. So you can hardly remove maybe 5-7 pixels, that's all. So in some domains, this kind of feature reduction techniques even don't work at all. So remember, there are 3 things, guys, and do not overestimate this power, okay? That then I can just reduce any feature. No, sometimes even with all this knowledge, you can totally fail.